First of all, I would like to thank the organizers for putting together this interesting conference and also for inviting me. I'm sorry that I cannot make it in person. So in this virtual talk, I will talk about something that we are very excited about recently. It's a new type of critical spin liquids. And the work was collaborated with Liu Junzhou, who is a postdoc at Parameter, and also Chong Wang, who is my colleague at Parameter, and they are the true heroes of this story. Okay, so and the paper was posted and also published last year. Okay, so let me start with something pretty general that we know we condensed matter physicists are studying phases and transitions, and that they are indeed one-way realization of the fixed points of quantum field theories, either attractive or repulsive fixed points. And indeed, you can make one-to-one correspondence for most, if not all, known or studied phases and phase transitions to the fixed points of QFTs. And for example, the Z2 spin liquid, the gapped topological Z2 spin liquid is one topological quantum field theory. And the critical spin liquids that is the topic of in this talk correspond to the conformal field theories in the language of QFTs. So once we are talk about QFTs, one of the first few words that may appear in your mind is the so-called renormalization or renormalizability. So in the textbook of QFT and also in people's most daily research on QFTs, we are always thinking about studying renormalizable Lagrangians. There are a few items to check in order to define a renormalizable Lagrangian. The one thing is that it should be a continuous theory, right? And secondly, the theory should be weakly coupled in the UV. Like you start with a Gaussian theory that is free, and then you turn on some infinitesimal relevant perturbations, let it flow into the IR. That's how people define renormalizable Lagrangian. But if you compare that with the condensed matter system we are studying, it's quite opposite. For the most cases, we're dealing with like discrete space, like lattice. And on the lattice, we have strong interactions in the UV, right? Like we have spins interacting with each other on the lattice, right? They're very different from renormalizable Lagrangian. So, and it's pretty amazing to say that two opposite setups eventually in the UV eventually give you the same universal physics in the IR. So that's pretty amazing. And sometimes it's a very natural thing to do if you consider, let's say, a symmetry breaking order as well as the transitions. Usually you can write down this Ginsburg Wilson-Fisher type of theory that is just 5-4 series, and it's a renormalizable theory. And then you can study its properties in the using QFT techniques, and physically you will find that you can easily say that this phi field is really just order parameter in the of the condensed matter systems corresponding to symmetry breaking and so on. It's pretty nice descriptions and very natural theory to consider. But sometimes it will become awkward or unnatural to use renormalizable Lagrangians to describe phases. And the typical example is a spin liquid that is one of the main topic of this conference. And particularly if you would consider some strongly interacting critical spin liquid, like the Dirac spin liquid, that has Dirac fermions interacting with a U1 gauge field. So this again is a well-defined renormalizable Lagrangian. But we know that although those fermions and gauge field, you can define it in the UV of a field theory, but the gauge coupling is relevant and it will drive the system into the strong coupling limit in the IR, which makes the fermions and gauge field are not sensible anymore. sometimes you will say that in this system, you don't have well-defined quasi-particles and so on. So that means, yeah, for this theory, indeed, or for this phase of matter, indeed, in the IR, the gauge field and fermions, that is usually called spin-ons, does not really exist. But on the other hand, so to study this phase in condensed matter systems, we conjecture they appear in some spin systems. Again, there's no fermions, spin-ons, or gauge field in my UV at all. So then it's really awkward that we are using some degree of freedom that spin-ons and gauge field, which does neither exist in the UV nor IR to describe this phase. So it's not quite satisfactory, but that's what we have to do if we want to really use some renormalizable Lagrangian to understand this phase. So, and this talk, what I'm going to do is that I'm trying to go beyond this renormalization paradigm. I'm thinking about some theories which are not renormalizable. You may feel uneasy about it, but as you will see that we will get a lot of good things out of it. And one nice thing is that for this Dirac spin liquid, indeed, we can find a rather intuitive descriptions, just use order parameters of symmetry breaking order. And that, yeah, it's in some sense, it's really a Landau-Ginzburg type of physical understanding of the Dirac spin liquid. And that's nice. And on the other hand, it also enables us to explore some phases, particularly critical spin liquid, that was not known before, and they typically does not. So we call those as non-Lagrangian spin liquid, or non-Lagrangian phase, meaning that you cannot find a renormalizable Lagrangian to describe it. And indeed, in string theory or high energy physics, there are also some CFTs which people believe that are non-Lagrangian. So it's not a crazy thing, even for those serious people studying QFT. Okay, so after this rather long motivation, let me start the main body of my talk. So I will first give you some introductions, and then I will talk about Dirac spin liquid, and I will tell you that how to understand it just using the physical order parameters you can observe in experiments and also numerics. And if I have time, I will then talk about the generalities of Stiefel liquids. As I said, it's a new type of critical spin liquid that we believe is beyond the conventional Whiston, like it's non-Lagrangian, and you cannot describe it using gauge series or spin-ons at all. Okay, so let me start with something very simple that everyone familiar with. That is this spin 1/2 Heisenberg chain, which I also talked about last week during my lecture. So, and we know that for this spin 1/2 Heisenberg chain, it's exact-solvable, and its ground state is a critical phase of a conformal field series. People usually call it 1+1, the critical spin liquid. There are experiment materializations, and there are also very nice experiments showing almost perfect agreement with theoretical results. Okay, it's a very nice example of a critical spin liquid, and there are many descriptions for people to describe this critical spin liquid theoretically. And one useful descriptions for one description useful for this talk will be this so-called nonlinear signal model descriptions. So one thing I forgot to mention is that this critical spin liquid is described by this SU2 level 1 Westrup-Witten CFTs. And for general SU2 level K Westrup-Witten CFTs, you can write down a nonlinear signal models with a unit 4-component unit vector. And physically, it's very easy to identify what are those 4-component unit vectors. The first 3 component is nothing but the spin order, spin moment. And the last component is the valence bound solid order. So, and with this, and usually we just call this N field as the order parameter field in the nonlinear Sigma model. And the first term is this kinetic term. And second term is a topological term that is called Westrup-Witten term. And as you know, this model is defined in 1+1 dimensions, but the Westrup-Witten term is indeed defined in 1 dimension or higher. And the boundary of this higher dimension of 3-dimensional manifold is our 2D 1+1D system. And this nonlinear Sigma model is indeed renormalizable in 1+1D. And people can solve it exactly and find that at 0 coupling, you get a Gaussian fixed point. And the Westrup-Witten term is indeed a relevant perturbation. And it will drive, once it's non-zero, it will drive the Gaussian fixed point into a conformal fixed point that is called SU2 level K, Westrup-Witten term. And this level K should be integer value because it's related to, because this term is a topological term. Okay, so this theory may seem abstract to you, but indeed, there are a few important things, and also it's rather physical that I will explain in a few minutes later. So first of all, as I said, the Westrup-Witten term is very crucial for this story. Theoretically, it actually modifies the Argy flow. If you don't have Westrup term, you just have this pure nonlinear Sigma models. And this theory is known to just flow to infinite coupling, which is the trivial gapped disordered state. That's nothing really interesting there. But if you have finite non-zero Westrup-Witten term, then it will flow to a conformal fixed point that is SU2 level K, and for K equals 1, that is a spin 1/2 Heisenberg chain. Okay, so and the physics of Westrup-Witten term is actually very interesting. It tells us the so-called intertwinement of the spin ordering and the valence bound solid ordering. So remember that this N field is a 4-component vector. 3 of them are spin moment, and the 4th component is a valence bound solid. And this, if you can indeed derive that the physics of this Westrup-Witten term tells me a picture like this. So if I draw a domain wall of my valence bound solid order, and as shown here, and in the center of this domain wall, there will be spin 1/2 trapped there. That's precisely the meaning, the physical meaning of this topological Westrup-Witten term. So, and in other words, yeah, this critical spin liquid or this CFT comes from the intertwinement or computation of spin ordering and valence bound solid. And the last thing I want to highlight is that, as I said, it's a topological term. So then the topological arranging of it comes from the homotopy group of the manifolds that the order parameter field lives. It's a 4-component unit vector. So then this unit vector lives on S3, 3 sphere. So then you can. So we know that the 3 sphere has Z integer valued pi3, and it's the pi is a homotopy group, tells you about the winding number, let's say, and pi2 is 0. So this is the topological arranging. Only with this you can define the Westrup-Witten term. And remember, this K is integer valued, and that's indeed correspond to this Z valued pi3. Okay, so this is story in 1+1D, and now what we want to do is that we want to go to 1 dimension higher. We want to consider 2+1D physics. Okay, and a very straightforward generalization would then just increase one component to my 4-component unit vector, then I will have 5-component unit vector. And then, in other words, this new order parameter field will live on S4 for sphere. And since we are considering one-dimensional higher, this homotopy group should also like increase by 1. And we know that the pi4 of S4 is Z valued and pi3 of S4 is 0. So with this, then we can define a Westerm Norwegian term. So for this, so then we can write down a 2 plus 1 dimensional Westerm Norwegian model. But different from 1 plus 1D, this model then indeed is non-renormalizable for if we want to consider any fixed point other than the symmetry breaking fixed point. So at 0 coupling, this theory will just spontaneously break my global symmetries. In other words, this N field will get a finite expectation value, and the ground state manifold is just the S4, the target manifold, target space of the nonlinear sigma model. We know that in 1 plus 1D, that won't be the case because due to the Mermin-Wegener theorem. So, but in 2 plus 1D, we will have symmetry breaking. But what we know from many other examples, similar examples, we know that if you increase the interactions, and if the interaction strengths hit some critical value, then you will have order-disorder transitions, as drawn here. And after the order-disorder transitions, the theory will flow to some disordered fixed point. So, and our conjecture is that this disordered fixed point will be a conformal fixed point. There are a number of arguments or physics, physicists prove to convince ourselves that it is a conformal fixed point. And if you just compare those two situations between 1 plus 1D and 2 plus 1D, the only difference is that the Gaussian fixed point in 1 plus 1D gets splits into 2 fixed points. One is symmetry breaking fixed point, and the other is the order disordered transition fixed point. And this indeed happens in many examples, like just the Wilson-Fisher type of nonlinear sigma models, where you can do 2 plus epsilon expansions to show that indeed happens. And what we conjecture is that this conformal fixed point is intact if in this 2 plus 1 dimensions as well. And this is the safety at this fixed point is that we want to study. Okay. So so then we can ask, what is that conformal fixed point that I discussed in this SO5 nonlinear sigma model? And it indeed is a very famous transitions that called deconfined phase transitions. Called deconfined phase transitions. Somehow I think my slides is not shown properly. Let me see. Oh, no. Okay. Yeah, somehow it's my fault. Okay. So yeah, so this is so-called deconfined phase transitions. So remember that we have the 5-component unit vector for this nonlinear sigma model. And similar as 1 plus 1 dimensional example, the first 3 components are just a spin ordering, and last 2 components are the valence bound ordering. And different from 1 plus 1D, the reason that we have 2 components as opposed to 1 component is that in 2 plus 1D, let's say on this square lattice, I can have 2 different types of ordering along X direction or Y direction. That's I get 2 components. Okay, and again, you can easily understand the physics of this Westerm Norwegian term. As I said, it's an intertwinement between those 2 different ordering, the magnetic order and the valence bound solid order. And the way to say it is that you just, again, draw the domain wall of the valence bound solid, as shown here. And in the center of the domain wall, you will find that there's a spin half trapped there. So this, again, nicely tells us about the physics of these nonlinear signal models, as well as the deconfined visualizations. Okay. And historically, you may know that at the beginning, people was using some gauge theories like spin-ons, bosonic spin-ons, coupled with a U1 gauge field to describe these deconfined visualizations. But as I would say, it's not really intuitive because you cannot really quite say the spin-ons or gauge field. And from this theory, you don't see this emergent SO5 symmetries that people have observed numerically. But in this nonlinear signal model descriptions, everything is pretty physical. You just think about all the parameters and think about the domain walls of all the parameters and so on, then you would understand the essential physics there. Okay, so and let me just recap what I described are two nonlinear signal models in 1+1D and in 2+1D. And the target space of my order parameter field that just lives on sphere, like 3 sphere or 4 sphere. And those order parameter field has very nice physical meaning, as its name suggested. They just correspond to, it's just a combination of a magnetic order and the valence bound solid order. And the important ingredient in this story is a Westerstrom-Witten term, and physically, it also has a very nice meaning that it tells me how the order parameters, different order parameters are intertwined together. Like if you create a domain wall of one order parameter in the center, you will find another order parameter. Yeah, it's pretty intuitive for us to visualize those conformal field theories. Okay, so now let's move on to more non-trivial examples. That is the Dirac spin liquid. And as you may know that the Dirac spin liquid happens in the frustrated magnets. Okay, like triangular or Kagome. And typically in those frustrated magnetic systems, the magnetic order or valence bound order we'll find is a bit more complicated. And one famous example is this 120-degree order, as drawn here. And you can also find some complicated looking valence bound solid. Like here, this is called root 12 by root 12 VBS. And then let's just play the game that we played before, that we first asked what are the order parameters. So for the magnetic order, the order parameters will, for this non-collinear magnetic order, the order parameter will be 6 component. In other words, you can write down 2 orthogonal 3-component vector, like here, to describe this magnetic order, right? And this valence bound solid order also have 6 components. And you can easily convince yourself by looking at the ordering momentum of this valence bound solid. You will find it's located at 6 points in your gradient zone. That's why its order parameter is 6 component. Okay, so and now the idea is very straightforward. Let's say if we intertwine them together or make them competing, what will happen? Can we get something similar as the 1+1D Heisenberg chain or the deconfined visualizations? Okay, and as you know, for deconfined visualization, we have this 3-component collinear magnetic order at this simple valence bound solid, which is 2-component. Then we get 5-component vector. We put it on a 4 sphere, and then everything works, right? We get a right homotopy group that I can define a Westerstrom-Witten model. So now, what if we just do a very naive generalization? We just put those 6 components, those 12 components of order parameter together, makes it lives on the 11th sphere. But can I get a Westerstrom-Witten? But then you can easily realize that this won't work because S11 has a non-trivial pi 4. So then you cannot define Westermann-Witten term at all. So then we should do something smarter. And it turns out that the way to generalize it will involve this. We should use this so-called Stiefel manifold, which abstractly written as SON quotient SON minus K. So it may not be familiar to you, but it's indeed a very simple manifold to visualize. So you can just, this manifold can be parameterized by K mutual orthogonal n-component unit vectors. In other words, you can just write down an n by K matrix, real matrices, which satisfy these orthonormal conditions. That's it. And the sphere is indeed just a special case that you consider SON plus 1 quotient SON. In other words, it's n plus 1 component unit vector, right? The next non-trivial example is that you can consider SO6 type quotient SO4, and that's really just parameterized by two mutual orthogonal 6 component unit vector, and that's it. So it's a very simple manifold indeed. Okay, so now just as I said, this V1 half Heisenberg chain and deconfined differentiations, they are indeed just special examples of Westermann-Witten models on Stiefel manifold. That sphere, because sphere is a Stiefel manifold. Okay, and but with this Stiefel manifold, then we can generalize it to a family that is SON quotient SO4, because for arbitrary n larger than 4, we always get a non-trivial pi 4 that is z-valued and trivial pi 3. So then for this manifold, we can always define a nonlinear Westermann-Witten models, and then we can, with a number of arguments, we conjecture that its phase diagram of that nonlinear sigma model will look like this. There will be some ordered phase with the ground state manifold to live on this Stiefel manifold. If the interaction is strong enough, we'll have an order disorder transition, after which we'll get a conformal fixed point, which is totally disordered, no symmetry breaking. And we call this conformal fixed point as the Stiefel liquid. Yeah. Okay. So, and it turns out that, so for n equals to 5, that's really just deconfined phase transitions. And it turns out that for n equal to 6, that's the correspond to the physics that we intertwine this non-collinear magnetic order with the with this root 12 valence bound solid. Okay, and with a bit more work, we realize that indeed this n equal to 6 Stiefel liquid are really just a so-called Dirac spin liquid that people has been studied a lot in the past. Okay, and the conventional way to get this Dirac spin liquid is that you do some Pardon constructions that fractionalize the spin into spin-ons, and then you put it into some band structures that have Dirac cones, and then you end up with a gauge series that has 4 Dirac fermions interacting with a U1 gauge field. That's the story of the, and that gauge theory is also called QT3, which is renormalizable. And that's the conventional way for people to study the Dirac spin liquid. But that description may seem obscure, as you don't quite see how it's make contacts with my microscopic spin systems. And later, indeed, we realized that in this Dirac spin liquid, the key thing is that the monopoles of that gauge series, and the ordered phase comes from the condensations of the monopoles, and those monopoles are indeed the order parameters of this non-collinear magnetic order and valence bound solid. And in our this Stiefel liquid language, those monopoles of the gauge series is nothing but my order parameter field that I use to write down the non-linear models and Westermann-Noether terms. And physically, those monopoles just correspond to the non-collinear magnetic order and this valence bound solid. Yeah, one thing you can easily check is the number matches, right? In total, I get 12 components. And remember, for the Stiefel manifold, this SO6 quotient SO4, as I showed before, is 2 mutual orthogonal 6-component unit vectors. So in total, I also have 12 component unit vectors, 12 component order parameters that matches the number of its order parameters of those 2 different symmetry breaking orders. There are also a number of non-trivial checks that we did in our paper. Okay, so, and I want to mention that this Dirac-Spin liquid has been found to, there are a number of numerical evidence suggesting that this Dirac-Spin liquid exists in various microscopic models, like this Kagome-Heisman model. One of the organizers, Yasir, did very nice work on those 2 models, and the other is this J1J2 triangular model. And particularly in J1J2 triangular model, we know that if you only have first neighbor interactions, you will get this non-collinear magnetic order. And in our picture for this Dirac-Spin liquid or Stiefel liquid, physically it really comes from that you intertwine this non-collinear magnetic order with some valence bound solid, then you get this Dirac-Spin liquid. And there are some candidate materials to realize this Dirac-Spin liquid as well. Okay, so then I will talk about the more non-trivial examples of this Stiefel liquid, and I will say it's a new critical spin liquid. So how am I doing in terms of time?
You can continue. We have 5 more minutes and then some discussions if you want to leave some time for discussions.
Okay,
5 to
I will.
10 minutes. 10 minutes, yeah.
Okay, thank you. Yeah, I will try to keep it simple. Yeah. So just recap what I said. So we define a Westermann-Noether models in 2+1D, and the key player is that to use this Stiefel manifold that is SON quotient SO4, and as I explained, don't feel scared about this abstract manifold. It's really just an n times n minus 4 matrix, which satisfies some orthonormal conditions, and that's it. And and physically this n field corresponds to the order parameters of the symmetry breaking orders that we can find in the microscopic system. And the conjecture is that for this nonlinear signal models at finite coupling, we will get a conformal fixed point, and and we call it Stiefel liquid. And so for this, and we believe that for different integer value k, we will get different, let's say, CFTs. And for n equal to 5, k equals to 1, it's a deconfined phase transitions, and you can easily identify the order parameters. This n field in my microscopic systems, they are just magnetic order and or valence bound solid order. And for Dirac-Spin liquid, we get more order parameters. That is, this n matrix will have 12 components, and 6 of them will be this non-collinear magnetic order, and 6 of them will be this valence bound solid. It's pretty physical and easy to visualize. Okay, now we want to do something more exotic, that we go to a slightly higher n, that is n equal to 7. So, and we ask, what could this guy be? And for n equal to 7, there will be 21 order parameters. So then we should play with a more complicated order parameters. And it turns out what we need to do is that, so just consider more complicated magnetic order. Remember, yeah, I'm just repeating what I said. For this n equal to 5, the order parameter we have, the magnetic order we have is a collinear magnet, right? That's deconfined phase transition. For Dirac spin liquid, the magnetic order we have is a non-collinear magnetic order, right? And the next natural thing you want to consider is a non-coplanar magnetic order, right? That have spin ordering moment to be non-coplanar, as shown here. So for this, you indeed get 12-component order parameters. You get 9-component order parameters here. And then you want to consider two different types of valence bound solid, which have 6 components each. And then in total, then you will have 21-component order parameters. And physically, that may give you this n equal to 7 Stiefel liquid. So, and our conjecture is for n larger than 6, although this Stiefel liquid will be non-Lagrangian. That means you cannot really write down a renormalizable. So this conformal fixed point exists. You may describe it using the abstract algebra of a CFT, but you cannot write down a renormalizable Lagrangian to describe it. Okay, that's our conjecture. There are a number of reasons that make us believe that might be the case. So for this Stiefel liquid, indeed, even so, we defined using this nonlinear signal models. For this fixed point, this model is non-renormalizable, but there's still a lot of things we can see about this conformal fixed point, this Stiefel liquid. One thing is that the global symmetries of this theory. So you don't need really to read this rather heavy slide. It's a bit technical, and for this talk, and also we can get the anomaly of this Stiefel liquid. Again, it's a technical result, but I guess. And then we can think that whether they would, whether they could emerge in condensed matter systems and how it could emerge. And the key is to consider anomalies and symmetries. So, and then with this, we can indeed even have so the idea is do something like an anomaly matching and to compare the lattice system and the IR anomaly of this CFT. So, and in the end, we can indeed get a full classifications of Stiefel liquid on all the 2D lattices. That was achieved. That was done by the heroic effort of a student, Yin-Chen at PI. But I was very quick on those slides, and as I said, it's rather technical, but I guess so one key message is that I want to deliver is that I give you a very nice physical picture about how to visualize this Stiefel liquid, and we also did very serious studies, theoretical studies on the properties of the Stiefel liquid and discuss when they could emerge in condensed matter systems. And the key message is that physically, to think about those Stiefel liquids in quantum magnetism, it's some critical states that emerge from melting or intertwining different symmetry breaking orders. That's the physics there. And it's a very nice cartoon picture. And we can have rather serious and sophisticated, using some serious and sophisticated math to really understand its natures and emergence in condensed matter systems. And physically, for this n equal to 5, k equal to 1 Stiefel liquid, it's also called deconfined phase transitions. The way to realize it is that you just intertwine or have the computation between a collinear magnetic order and a valence bound solid. And for n equal to 6, that is a Dirac spin liquid, what you do is just make the consider a non-collinear magnetic order with a valence bound solid. For this n equal to 7, this new critical spin liquid, what you do is that you consider non-coplanar magnetic order instead, and some valence bound solid. So this also gives us, not just gives us a physical picture about those Stiefel liquid. On the one hand, it tells us how to experimentally measure those Stiefel liquid. What you want to look at is just try to find a way to measure the critical mode of the spin ordering, as well as the valence bound ordering, right? And this also gives us a way to find them in either experiments or numerics. So the way is that you first you may want to find some ordered phase with this pattern, and then you want to add interactions or add interactions that say try to melt this specific symmetry breaking order, and in the end you may get the critical spin liquid that we want to have. And it turns out, and this strategy actually works for both deconfined visualizations as well as the Dirac spin liquid. Right? And it will be interesting to know if we can also find Stiefel liquid just by considering non-coplanar magnetic order instead. Okay, let me just summarize. So I introduced a family of critical spin liquid that called Stiefel liquid, and it's a Westermann-Witten models. And the key player is the Stiefel manifold SO1 quotient SO4. And this unifies deconfined visualizations and Dirac spin liquid. And we also, so it's an infinite family of CFTs or critical spin liquid labeled by integer valued n. And for n larger than 6, we conjecture that they are possibly non-Lagrangian. At least we cannot find any known theory to describe this Stiefel liquid. And its physics is actually the simplest one. It has a very simple physical meaning that is just intertwine non-coplanar magnetic order with valence bound solid. And yeah. So thank you for your attention.
Let's thank Yin-Chen for a very nice, insightful talk. Questions? Yeah, Johannes.
Yes, thanks. So I have a question. I'm a little bit confused. So you say the Dirac spin liquid. So I shouldn't think of spin-ons coupled to a U1 gauge field. But if you, for example, compare to the numerical work of Yasir, or if you look at the prediction for what we would expect for specific heat and so on. So, it works rather well to think of these Dirac cones of emergent fermions. So, yeah, how do you does that fill in with?
Yeah, for example, for specific heat is a universal fixture for any 2 + 1 DCFT. No matter you have Dirac fermions or gauge field, or even just a Wilson-Fisher type of symmetry breaking transitions, you will always get the same specific heat. Mm-hmm. Yeah. All those are really just universal features of CFTs, not special for Dirac fermions and so on.
Okay, and so then the second part is can you also within the nonlinear sigma models predict critical exponents, which then would
no.
Oh,
even for renormalizable Lagrangians, you cannot really predict critical exponents. You can have some perturbative calculations.
Oh, I mean, at least in some 2 + epsilon, or some epsilon expansion.
Yeah. For this, no. That's why it's non-renormalizable, right? you can only do perturbations if it is renormalizable, right? But in the end, the hope is that, I mean, that's hope of many people studying conformal field theories, is that we don't want to do perturbative calculations. We really want to understand the operator algebra of that CFT, just like what we did for 1 + 1D conformal field series. No Lagrangian, no perturbations, everything is exact. That's a goal for for this Stiefel liquid or high dimensional CFTs. We just care about the intrinsic properties like symmetries, anomalies, and algebra. Yeah.
Okay, thanks.
Hi, Yin-Chen. I have a question on the introduction and also afterwards. The first question is this: your SO5, right? So you have your SO5 nonlinear sigma model of Wessel-Wiener-Witten term, level K, and then you say very quickly that there has to be, this Lagrangian could in principle have just an ordered state. It's highly non-trivial to claim that it has a CFT, no? You sort of gave the impression you gave the impression that you had some proof for that. So
so for this model per se, there are some there's some way to justify it.
How do you justify that there's not? I mean, we did some simulations for that, and it was non-trivial to. It was the outcome could have been just a symmetry broken phase for every time for all.
Yeah. That's true. So there are few things people did in the past. I guess you also know many of them. So right. One thing is that you can consider 2 plus epsilon expansions for this two models. Like you can connect those two. That's a work by Chong Wang and his student.
Right.
So then there you will say that at 2 plus epsilon, this Gaussian fixed point gets split into two fixed point, symmetry breaking and all the disorder transitions. So, and in that calculation, you can find that the SU2 level K, I mean, this conformal fixed point are still there if epsilon is small.
Okay.
But to Johanna's question that for this particular example, we can also get critical exponents just using this nonlinear sigma model. But for generic case, no, it's a complicated model. It's a matrix model indeed. Yeah. So but the situation is that there's one scenario, one possibility is that this disorder transition fixed point will collide with this conformal fixed point.
Right.
That's totally plausible, and that is what you describe. I guess that's what you had in mind, right? So for the deconfined phase transition, what we believe is that those will collide, and then everything disappears. But for generic case, in particular, for this family of Wessel-Wiener-Witten models, like this Stiefel manifold, what we believe is once n is large enough, then those two fixed points will not collide. For small n, they will collide. Yeah.
So then the second question is, I mean, for the SO5, you could start with Dirac fermions and have anti-commuting, a quintuplet of anti-commuting mass terms, and that will give you a very easy way to start with fermions and generate this. Can you do that also for the generalizations for the n equals 6?
For Dirac liquid, we can do that.
But for the n equals 6 or n equals 7?
No, that's why we think it's non-Lagrangian. So indeed, there's something very fundamental inconsistent with the Dirac fermions. So yeah, so since Farha asked, so let me say a little bit about this business. So we can consider, let's say, Dirac fermions coupled with some gauge field, right? Like U1 or SU2, whatever, right? And then you integrate Dirac fermions, you get some nonlinear models. That was Farha was asked. And for all those gauge series, you indeed end up with a Grassmannian manifold, not Stiefel manifold. It just happens to the case that for n equal to 5 and n equal to 6, the Stiefel manifold is equivalent to some Grassmannian manifold, just due to the the isomorphism between the small Lie group. But it doesn't happen for n larger than 6. So yeah, that's indeed one reason makes us to believe that n larger than 6 Stiefel liquid does not have Lagrangian descriptions. Does this answer your question?
Yeah. Thank you very much.
So can we introduce temperature dependence in your theories? Like for QFT, you use temperature dependent, and we get thermal field theories because.
Yeah, I think so. I'm not entirely sure what you have in mind, but what we think is that this Stiefel liquid is a CFT, right? So then whatever you can do for a CFT, you can do it for Stiefel liquid. like for example, for temperature dependence, for example, the specific heat dependence, it's universal for any FT, including free Dirac Fermions, symmetry breaking transitions, Dirac spin liquid, as well as those Stiefel liquid. And there are also some other features if you turn on the temperature, but you just think it in terms of conformal field series.
Sorry, Yin-Chen, I have a quick question. If I understand your prescription for obtaining n equals 7 Stiefel liquids, is that one must look for model Hamiltonians, which could be host to non-coplanar magnetic orders, right? And then once you meld those orders, there's a possibility of realizing those.
Exactly.
On the Kagome, there's been a lot of work on the Heisenberg models with long-range interactions, as you know, by Donna Sheng and others, where you have some Q-Borg type orders which melt and give rise to possible chiral spin liquids, right? But if I understand, for you, in your case, you have symmetric spin liquids in mind, right? So, I mean, has there been some exploration whether these domains in Kagome parameter space could actually be host to Stiefel liquids because the parent order is non-coplanar?
Yeah, I would expect so, and and with some collaborators, we are working on this slowly, but so far there's some signals, but there's not really.
Okay, and do you think that they admit some simple parton description in terms of Abrikosov pseudo-fermions for these n equals 7? No.
No. That's the whole point of it's non-Lagrangian.
Right.
Yeah. It just,
is there any other fractionalization scheme? I mean, in terms of no. Okay.
No. After years of thinking about CFTs, I finally convinced myself for those critical spin liquid, the fractionalization is not the right way to go. It's bad to go back to the order parameters that we don't like in the past.
So in the interest of time, since we're already behind, I mean, let's thank Yin-Chen again for a very engaging talk.
Thank you.
Yeah, thank you so much again. And next time we hope to see you in Bangalore.